All right, we're still in Unit 3, Lesson 3, set questions, but this video starts at number 11. So for each of the following functions, find the desired features. And we're given a graph with some context. So this function represents position relative to the surface of the water for the last few minutes of a person's snorkeling trip. If you've ever been snorkeling, you know that you can go underwater a little bit. You just don't want to get water all the way in your snorkel. If you do, you better blow it out before you inhale. So the position is going to be, or rather position relative to the surface of the water is going to be what is on our y-axis. I don't know what's going on with my computer, why it's not letting me highlight, but I think it's mad at me for making so many videos. And then time. Now, we know time is measured in minutes. Well, yeah, we know time is measured in minutes because it says the last few minutes. So time in minutes is going to be what's on our x-axis. So if we think about this, position relative to the surface of the water, a negative position down here, like negative values, this would imply that we're under the water, like under the surface. Positive values would imply that we're above the surface, just to like make sense of this graph. Okay, we're asked to identify the domain of this function. So for the domain, again, that's going to be all the x values where this function exists. And I'm going to use interval notation. And so just to be clear, I'm going to put a closed circle on the ends of this. We don't see arrows and we don't see an open circle. An open circle just looks like a washer, I suppose. It looks like a circle that's not filled in. So that tells us that our function starts at this x value and ends at this x value. And for ease of us talking about this, let's just assume that this x value is at it looks like it's really at about 13.5, 13.5. I'm going to assume that that's 13.5. We don't really have enough information to know. So my domain begins where x equals 0. So this function starts where x equals 0, and I'm going to include 0 in my domain. And then as I continue, as I kind of trace, I don't know if you can see my cursor, but I'm kind of tracing the function. It never has any interruptions. It never has any discontinuities. So there's no break in the domain, and the function's not discrete either, meaning that we've connected all of the points along the curves and the lines. So that means that the domain continues without interruption to the x value that I am just calling 13.5. But again, we don't really know for sure there. We're just kind of estimating that. All right, so domain, we said that's going to be our x values where the function exists. Our range is similar. That's y values where the function exists. I think it helps me to actually talk about the maximum and minimum values first. So we said a maximum and a minimum are both y values, but we sometimes identify where they're located. So the maximum value will be the greatest output of this function, and that occurs over here. Well, it occurs right here, but on my y-axis, that is where y is 3. So my maximum is the number 3, and that occurs at x equals 13.5. So sometimes we refer to this as the location of the maximum. Where on the x-axis does the function achieve its maximum value? And it can happen more than once, but in this function, it only happens at 13.5. The minimum value is going to be the lowest number, and it looks like it's about right here. And again, we're just going to have to estimate this because we don't know for sure, and we do not have enough information to find out. So we know it's a number between -3 and -4. I'm just going to go with -3.75. It kind of looks like it's 3/4 of the way between -3 and -4. If you wrote something a little different here, that's okay because we don't know for sure. as long as it's close to like about negative 3.75, maybe you wrote negative 3.8. And again, we could say that that happens at the x value, x equals 1. So again, 1 would be where the minimum is located, but the minimum value itself is the output, the y value. All right, so now when we're talking about range, our range is going to include my lowest y value, so my minimum value. I don't really know why I said lowest. I was looking at the graph, negative 3.75, and then my range goes all the way up to my output of positive 3. So when I'm looking at my range, it's I'm looking at the range of values from my minimum to my maximum. All right, when we're talking about intercepts, we have two types of intercepts. We most commonly talk about the y-intercept, and that is the point where our function is on the y-axis. So this is always where our x value is 0. So on my y-axis, I see this point. I'm going to estimate that that's at negative 3.5, so negative 3.5. So I could write my y-intercept as an ordered pair, 0, negative 3.5. So this is not interval notation, it's an ordered pair. And we know that because we're talking about an intercept. So we kind of have to infer from the wording that that is at 0, negative 3.5, and that is an ordered pair, not interval notation. I understand they look the same. It can be confusing. We just have to read carefully. But we also have another type of intercept. We have an x-intercept here. And our x-intercept is going to be where our graph exists or crosses at the x-axis. It doesn't have to cross, it just has to be on the x-axis. So remember, the x-axis is where all of our y values are 0. So I'm going to estimate this at about 12.5 because it looks like it's halfway between 12 and 13. We don't really know for sure. So I'm going to say my x-intercept is where x is 12.5 and y is 0. So remember, when we write an ordered pair, it's always an x and then a y. All right, intervals of increase. So I'm going to highlight in yellow everywhere this function is increasing. So when I start on the left, it's decreasing at first. So like my position relative to the surface water is decreasing from x equals 0 to 1. But at 1, it looks like we start to increase until we get to about 4, or maybe right at 4. Then the function decreases until, I'm going to say 6. It looks like it's about 6. And then my function's increasing. Here it changes, but it's still increasing. The y values are getting greater. And then when I get to the point at about 12.5, x equals about 12.5, I continue to increase here. So everything I highlighted yellow is an interval of increase. And remember, we typically don't include the endpoints of the intervals in our interval notation. So I'm going to, just to help me, I'm going to kind of draw dashed lines through where these intervals begin and end, just to kind of help me look at the x-axis. I know I've already got a dashed line here, that was green. So for my first interval, from x equals 1 to x equals 4, using interval notation, I could say from 1 to 4. Then when I want to join that with my second interval, I often use the union symbol. And if you learned about Venn diagrams, you know this is a union symbol. And in math, we actually kind of think of this as the word or. I know our brain wants to say and, but really in interval notation, it just will help us join the intervals where the function's increasing. So from x equals 6 to x equals 13.5, our function is increasing as well. So for intervals of decrease, I'm going to highlight the graph blue. So from 0 to 1, my values of y are decreasing. My position is decreasing. And from x equals 4 to x equals 6, I'm decreasing. So for those intervals, I'm going to I never know what color to pick. For those intervals, I'm going to say I'm decreasing from 0 to 1. I'm going to use my union symbol, and then from 4 to 6. So this shows me that the function's decreasing over the interval 0 to 1, and the function's decreasing again over the interval 4 to 6. I realize that it's confusing that looks like ordered pairs, but again, it's the context that tells us these are intervals. We were asked for intervals. All right, lastly, is the function discrete, continuous, or discontinuous? Well, we know it's not discrete because everywhere along the curves, along the lines, the points are joined. I don't see just like points existing in my table without them being connected. There are no discontinuities. So from x equals 0 to x equals 13.5, there's no place where this function doesn't exist. That makes this a continuous function. So this function is continuous across its domain. All right, the next two are a little bit harder. For number 12, we are given a sequence described by a recursive rule. And I'm going to assume that since we are given f of 1 is 42, that my first input in the sequence is the number 1. So I'm going to actually make a little table. It says find the first 5 terms of the sequence. I'm going to do that in table form. So my first 5 terms would be term 1, 2, 3, 4, and 5. In this recursive rule, we're told that when n is 1, my first term is 42. Also, looking at the other part of our recursive rule, we could see that I am subtracting 7 from my previous term. So I could either use the rule to evaluate. So I could say, like if I'm finding f of 2, I'm using what I highlighted in blue here. I'm going to start with f of 2 minus 1 and subtract 7. Well, that's the same as just looking at f of 1 and subtracting 7. So since f of 1 is 42, 42 minus 7 is 35. So I could just fill out this table by continuing to subtract 7. So I get 35, 28, 21, and 14. All right, so the domain, again, the domain is all the inputs. We sometimes say x values. In this case, we're using n instead of x, but my domain is the inputs where the function exists. So let me point out that it does not exist for all real numbers. We start at 1 and then we're only counting up using counting numbers. So I'm going to say this domain is natural or counting numbers. We sometimes use those two words interchangeably. But we said that is a subset of the real number system, and that's going to help us answer this question down here in just a minute. All right, my range of values, if I look at my outputs, the greatest number in my range is the number 42, and my range, like as I go on, I'm always subtracting 7, and so I know that my range, like my maximum value, is the number 42. So I'm not going to use set builder notation here, but I'm going to say my range, I'm always going to get integer values. So I'm going to say my range are going to be integer values that are less than or equal to 42. And so if you're like, wait, integer values, that includes negative numbers. Well, I know we only had to come up with the first 5 terms, but let's say I keep going. My 6th term would be 7, my 7th term would be 0, my 8th term would be negative 7, and this pattern would continue into the negatives. So that's why I use the word integer instead of whole number or natural number. All right, our maximum value is 42. because the function starts at 42 and decreases. But because it goes on forever, I never have a minimum value, because whatever minimum I get, I just subtract another 7 and now I have a lesser number. Okay, the intercept question could be kind of confusing without a graph, and I get that. For the intercepts, we said a y-intercept is where x is 0. In this case, I'm going to think of that being like n equals 0, but that could be where x is 0. And I notice in my table that I never plugged in 0. This function started when n is 1. So I'm going to say that there's not a y-intercept. But my x-intercept, an x-intercept, that happens where my y value is 0, or in this case, where f of n, the function value, is 0. So if I look in my f of n row, I did have to continue it past the 5th term to see a 0, but I do see that f of n is 0 when n is 7. So for my x-intercept, my x value is 7, my output, or my y value, is 0. And if I were to graph this, I would have a point on the x-axis at 7, 0. Okay, for intervals of increase, well, there are none. This function is never increasing. For intervals of decrease, I'm going to be a little lazy and say that this function is just always decreasing. I'm not going to write interval notation here. All right, lastly, is this function discrete, continuous, or discontinuous? This function is discrete because we're only plugging in natural or counting numbers. So in Unit 2, we defined a discrete function as having a domain that's like a subset of the real number system. Natural numbers are a subset of the real number system. That's why this is discrete. All right, number 13. I know this one's tough, but I think it's a really good problem to really assess what we know here. Okay, so I want to point out something kind of as we get started. You don't need to know this term right now, but we call this a piecewise defined function. And if you look at it, it's a function that looks like it's made up of pieces of a bunch of different lines. They don't always have to be lines. In fact, the function that we looked at up here is also piecewise, and it's made up of curves and lines. But if you break it up, we see just like all these different pieces. So we might come back to that term later this year, but for now, you don't really need to know it. It is what we call this though. So for my domain, I've got to be really careful here. To clarify something, where I see a closed circle, so a closed circle is like a circle that's filled in, the function exists there. Where I see an open circle, it does not. So like a washer or a circle that's not bubbled in. The function does not exist there. So if I were to ask you what is the value of this function when x equals -4, you would tell me that the value is 1 because I have a closed circle there. You would not tell me that the value is 2 because there is an open circle there. So as I get really, really close to -4 from the left, that's where I'm getting close to -4, but as soon as I'm at -4 on my x-axis, I'm going to jump down to this piece. And we actually do call that a jump, but we don't need to talk about that right this moment. All right, so as I'm looking at the domain, I said the domain's all the x values where the function exists. I'm going to trace this and then I'm going to delete this. So if you're following the video, I'm going to highlight, but then I'm going to delete what I highlighted. So it's up to you if you want to highlight this or not. If I start on my x-axis at -9, that's the first part of my domain. And then even though the function doesn't exist right there at -4, I jump down to this piece and the function still exists there because that was a closed circle. So like as I keep going, I get to another closed circle, but then something weird happens. I notice that between x equals 4 and x equals 5, the function does not exist here. But starting at 5 and including 5, because that's a closed circle, I'm going to keep going up. The function exists right there. When I get to x equals 7, I jump up to this other closed circle. The function continues to exist all the way to x equals 12. So I'm just going to label that 12. I'm going to label that 7 on my axis. I'm going to label my 4. Sometimes it helps me to fill in the values that I might think might be important. All right, so we define domain as everywhere the function exists. So the function begins existing at -9, and I'm including -9 in my domain because of the closed circle. And the function continues to exist until I get to 4. So even though I have what we call a jump here, that's just what we call a type of discontinuity, my function still exists there because of the closed circle at the bottom piece. So all the way from -9 to 4, my function exists. But it does not exist from 4 to 5. So I want to do the next part of my domain beginning at the number 5, and then my function exists all the way to 12. But there was a break in my domain from 4 to 5. So that union symbol, the thing that looks like a U, but it's not a U, it just looks like a U, that just tells me that these two intervals represent my domain. All right, before we talk about range, let's look at min and max. So my minimum value, again, that's an output, that's a y value. On my graph, I see it's right here. That is at -2. So I don't know why I started with minimum. I guess my brain likes to go from least to greatest. Y is -2 is my minimum, and that occurs at the x value, x equals 12. But the minimum value is the -2. My maximum is going to be my greatest y value, and that is at 7. So my maximum value is y equals 7, and that occurs at x equals 7. So the x values we call the location of the minimum and maximum. So my range is going to be my least y value to my greatest y value. So I'm going to say my range is from -2 to 7. All right, intercepts. Again, I'm looking for x and y. On the graph, it's a little bit easier to see. My y-intercept is right here on the y-axis where x is 0. So that's the ordered pair 0, 2. I'm going to label that y-int for y-intercept. I only have one x-intercept, but a function could cross the x-axis or touch the x-axis multiple times. Now, I really don't want to get into this in this particular video because it will take a very long time. But I'm going to tell you that this x-intercept really occurs at about 10.88, 0. And if you're like, hey, that looks like 11 to me, I know it looks like 11. It's not 11. And if you're wondering where I got 10.88 from, I'll just show you quickly. I'm not going to do all the math. I don't need you to do it all for this example or this homework problem. But if I look at this piece, this linear piece, if I use the slope to like write an equation for just this piece right here, if I think about my change in y, my rise, I'm going from -7 to -2. So I'm decreasing by 9. So my slope, the numerator would be -9. My run is from 7 to 12. So my run is 5. If that's my slope, if I were to write an equation in, let's say, point slope form. So my slope, I'm going to use this ordered pair, x minus 12, and then I would add my y value of -2 out to the side. The way I could actually figure out that this number is really 10.88 is if I substitute 0 for y, because we said our x-intercept occurs when y is 0. So if you solve this equation, you will get the value that I got, hopefully, unless I made a mistake. That is always possible. I really don't want to do that right now. I mean, we could. It's not that hard. I just don't want this video to be a year long. All right, I told you I was going to delete my highlights because I wanted to highlight my intervals. I'm going to delete that domain highlight too. All right, so now when we talk about intervals of increase, I'm going to highlight everywhere this is increasing in blue. So this segment is increasing from left to right. The y values are, well, increasing, and so is this segment. But we do have to mind the gap in our domain. Got British there for a second. Okay, so my intervals of increase, I don't really need to worry about the open or closed circle. I'm not going to include the endpoints of the intervals. So from -4 to +4, I'm increasing. But then we said from 4 to 5, the function doesn't exist. But then from 5, x equals 5 to x equals 7, I'm increasing. For my intervals of decrease, I'm going to highlight those, I don't know, green, I guess. It's this part and this part of the function. That's where we're decreasing, because from left to right, as I look at the graph from left to right along my x-axis, the y values are, well, decreasing. Okay, so when I write that interval notation, again, I'm not going to include any of the endpoints. So -9 is an endpoint, -4 is an endpoint. I'm using parentheses so as not to include them. And then I'm not decreasing again until I get all the way over to where x is 7. And from 7 to 12, I'm decreasing. All right, so lastly, is this function discrete, continuous, or discontinuous? Well, it's not discrete. I could see how we could get these things confused. It's not discrete because between the points, there are lines connecting them. But this is what we call a discontinuous function. So our answer here is that this is discontinuous. And here's why. We have what we called a jump here. That's a discontinuity. If I'm tracing this function, I have to like pick up my pen or pencil to get to this next piece. So when I have to do that, that's a discontinuity. As I continue over here, I not only have to pick up my pen or pencil, but I also have to move over an x value. So there's a break in our domain there. As I get here, I have another jump up to this next piece. So we call this a jump as well. And then as I keep going, I'm continuous until I get to 12. So this is a discontinuous function because of the jumps.